All right, so today, here's the more flashy title instead of the bland title that was presented in the press lineup. So we have the most compact system of planets, and these planets are all record setters for the smallest planets that have ever been discovered so far to date. And so as I go through this press presentation, the key words to keep in mind are compact and small. This is small in every single respect compared to our own solar system and compared to other known systems. And just to bring us all onto the same page, this is a lineup of various types of stars. You have A stars that are much more massive than the sun, like Sirius and Vega. There's our sun. There's a G-type dwarf. I will use the term M dwarf and red dwarf interchangeably. I will try my best to say red dwarf since that's the more colloquial term. But these are stars that are 1/2 to 1/10 the size of the sun. They are much smaller, fainter, and cooler, and hence their red color. The three planets, I just want to cut to the punchline, are shown here in the lineup that was shown just a month ago. This is an updated lineup of all of our Earth-sized planets that are known, unambiguously rocky planets that are known in the galaxy, including Mars and the Earth. And you can see that our three planets are situated very nicely between Mars and the recently announced Kepler-20e, which was a sub-Earth, the first sub-Earth-sized planet ever discovered. None of these planets are habitable. They're far too close to their stars, but they are tiny. The key features of this new lineup of three planets is that they're all orbiting the same star. These are the smallest planets discovered around a normal hydrogen-burning star. The outer planet is Mars-sized. This is the most compact system of planets ever discovered, with orbital periods less than 2 days. The inner planet orbits its star every 10.8 hours, meaning that it transits its stars twice every Earth day. This is the least massive planet host star that has ever been discovered. The star is about 13% the mass of our sun. This was discovered in Kepler public data that were released last January, and we confirmed the planets and validated their existence and their reality using ground-based observations from Keck Observatory and Palomar Mountain, including images that were taken back in the 1950s. That actually allowed us to determine the reality of the system. So overall, this implies, given that there are so few of these red dwarfs in the Kepler field, and that this planetary system emerged so readily from that small sample of planets, and given the fact that you don't see all planets with the transit method, so with the transit method, if you see one planet, it's kind of like cockroaches. If you see one, then there's dozens hiding. In the same case here, we see one planetary system around only a handful of these very low-mass dwarfs, and it implies that about 1 in 3 red dwarfs of this size have rocky planets around them. So this is a very exciting discovery. Just to reiterate, this is made by the Kepler mission, which is a 1-meter Schmidt telescope looking at a portion of the sky, 10 degrees on the side, near the constellation Cygnus, continuously monitoring 150,000 stars, making exposures every 30 minutes, and it's been going on for more than 2 years. The problem with our particular star is that red dwarfs, or M dwarfs, are very hard to characterize because they are so different from our sun. But this is important because the size of the planet that causes the transit is directly related to the size of the star. With the transit method, you see the area that is blocked, so you get a ratio of planet radius to star radius. So if you want to know the planet radius by itself, you must know the star's radius. And in this case, we did not know the star's radius to high precision. Most of our models of stellar structure are based on the sun, so there was no touchstone for a star this low. So that meant that a lot of the key physical characteristics of the star, its mass, radius, luminosity, its temperature, age, and distance, were unknown. Now, this is the problem. The solution is to turn to an amateur astronomer, a very good amateur astronomer named Kevin Apps. Here he is receiving his ASP Amateur Achievement Award earlier this year. He is a prolific planet hunter. He has 23 refereed publications, 46 planet discoveries, 49 as of today. And Kevin is an outstanding member of the Astronomical Society and absolutely key to our project because of his encyclopedic knowledge of stars. And when he looked at the colors and the other properties that we measured for our star, KOI-961, he sent us an email immediately and said, "Do you guys realize that you were looking at a twin of a very famous star called Barnard's star?" Barnard's star is one of the closest stars to the Earth, lying 1.8 parsecs away, and it actually has a direct radius measurement by measuring the angular diameter of this very nearby star to high precision. So we were actually able to take Barnard's star's properties, recognizing that it's a twin of the star that we were interested in, which is much more distant and too difficult to measure. And we were able to just take Barnard's star's properties, its mass, radius, luminosity, temperature, and transfer them one by one over to our star that had unknown properties prior to this point. So Kevin Apps, the amateur astronomer from England, broke this whole case wide open for us. What was left is for us to go to Keck and Palomar and invest a large amount of telescope time into the confirmation that these stars are indeed very closely twins, and to the extent that they weren't exact twins, how do we have to tweak the parameters in order to get the correct match for the type of star we were looking at. So again, here is the planet lineup. And what's interesting about this planetary system, as I mentioned, that it's very compact and small. So we were looking for, in a way of an analogy, we tried to compare it to the first hot Jupiter. But the scale was all wrong. The 51 Pegasi b, the first hot Jupiter that was discovered in 1995, wouldn't fit if you tried to scale all the semi-major axes. And so the comparison point that we came up with was actually Jupiter and its moons. Our central star is only about 70% larger than our planet, Jupiter. And the system of planets is very reminiscent of the system of Galilean moons around Jupiter. So overall, the system is very compact. The inner planet orbits at about 1 solar radius, and I'm showing that on this figure here. The sun is the big orange circle, sorry, the big yellow circle, and KOI-961, the red dwarf, is the little orange circle. The inner planet orbits at roughly 1 solar radius, but it's actually orbiting at 7 stellar radii. So when you look at it in terms of comparing it to the central star, it's like you took your shrink ray gun and you set it to 7 times smaller and zapped a planetary system. And so what we have here is just an overall planetary system that's shrunk down because the central star is so tiny. And so here is a beautiful, I just want to reiterate that 10.8-hour orbit of that inner planet. We would really like, we're going to apply for telescope time to observe 2 transits in one night. So we'll open up the telescope, observe 1 transit, go about our business, and make sure that we remember at the end of the night to grab the 2nd transit of that same planet orbiting its star. And so here's a beautiful artist's conception of the system. This is a flyover, or perhaps you're in your spacesuit standing on this lunar-like surface, looking inward to your very bright red star, or your very faint red star. But the star, because you're so close to it, at this distance would appear to be about 7 degrees in your sky, or 15 times larger than the sun in our sky. And you would have these 2 almost moon-sized bodies hovering large in your sky, showing crescent because they are like Venus inward of your orbit. And so again, the key points are here, and that's the end of my presentation.